All right. Well, good morning. I think we're going to get started here. It's about 9:04. Seems like the right time. So my name is John Wu. I'm an astronomer at the Space Telescope Science Institute just up the road. And today I have the pleasure to introduce, excuse me, to introduce astronomy and AI. So this is kind of the confluence of two, up till very recently, disparate topics. And so this is going to be kind of a detour from what the previous lectures have been like. There's going to be more of a high-level overview, and I kind of want to give you all just the greatest hits of astronomy. So before I get started, can I ask the room, how many of you have taken a college-level astronomy course? Not a single one. All right, perfect. Good. Well, we have a lot to cover then. The greatest hits then. Let's begin with this figure. So this is showing a schematic of sort of the Big Bang on the left, and going through time, you're basically progressing all the way to the present day. This is often shown in talks about cosmology. Cosmology is the study of our cosmos, our universe as a whole, on very, very large scales. And so we believe that there was a Big Bang really early on, which we can't see, but we believe the universe dramatically expanded, and thus it started off very hot and dense, but then it cooled rapidly, cooled so much that in the beginning of the universe, there's all exotic states of matter. And then you end up with basically the formation or the condensation of things like atoms. And so what an atom is really is a set of protons and electrons, which are kind of zipping around in a plasma fluid if it's very hot. But if it's cooler, then that atom actually kind of falls into what we call the energy well, the potential well of that atom. So it recombines with the atom and it emits radiation. So it gives off light. And this is actually the earliest thing we can see in our universe. This is now called the cosmic microwave background. But we think early in the universe, as the universe is expanding, it cools very rapidly. And then all these atoms basically condense out of nowhere, out of the plasma and the quark kind of gas there. And then you end up with radiation being sent out in every direction. This is sometimes called the surface of last scattering. And because it's basically the earliest we can possibly see into the early universe. Happened about 380,000 years after the Big Bang. And even though it started off as being radiating in the hard ultraviolet light, so very intense light, stuff that would burn your skin right now at about 91 nanometers, the universe expands. And what that actually does is it causes radiation and stuff like that to lose energy. Because basically you can almost think of it as stretching out the wavelength of that light. And so now it's actually at a very, very low energy. It's called the cosmic microwave background. So microwaves are kind of like in the radio frequency spectrum. And it actually gives the universe an ambient temperature of about 2.7 degrees Kelvin. So very cold now. Okay. And so we know we can get a sense of, how much the universe has expanded since then in order to go from something that's extremely, extremely hot and very, very high energy to now very cold. What happens, and I'm going to show a simulation of this in a moment, is that you basically have what sometimes people call the dark ages. Basically, nothing is really happening. Gravity is causing matter to condense over large scales, but eventually that gravity causes gas clouds to form, clump together, and then undergo runaway gravitational collapse. And when you get enough gas in one place, you actually create the formation of stars, right? Stars are when you condense gas into these little balls, which are so tightly packed that they can cause nuclei, which normally want to stay away from each other due to electromagnetic repulsion. But they are able to basically crash into each other and undergo nuclear fusion. And that nuclear fusion actually generates a lot of heat and a lot of radiation, a lot of energy, right? Nuclear fusion is actually what a star, is characterized by. So fusion is basically if you have protons or hydrogen in the early universe, you fuse that together, you get helium. You get helium, you can fuse that together and get beryllium and eventually carbon and oxygen and all the sort of heavier elements. Stars can also be thought of as factories that create these heavier elements out of the primordial, that is the early universe, hydrogen. In the beginning of the universe, you can't have really high energy, heavy elements, but you basically can create them in stars. Okay, so these stars now start, what do they do? In this case, you can see all these bubbles here, and you see this term, reionization. These bubbles are when stars sitting in this dark void, of just gas, neutral gas, they start to ionize, or basically they start to blast away all the electrons that are bound to all the hydrogen gas that's floating around here. And it actually unbinds all those electrons. And so because those stars are giving off immense amounts of radiation due to their nuclear fusion processes, they can kick those electrons back out of the atoms, and then you end up ionizing the universe over time. Basically, you create these bubbles, and the topology of exactly how this undergoes is not well known. It's actually an active area of research. And then you end up ionizing the universe. And the most interesting thing about that is that when the universe is ionized, it's transparent. You can actually see through it. Like we can go and see through it much more easily. If it's neutral, in this case, in the dark ages, it's actually opaque. And that's because you have all this gas lounging around. And if you're trying to look through it, that means a photon has to be able to arrive into your focal plane, into your eyes, or into your detectors in the telescope. But that's not possible to happen if everywhere is full of this neutral gas. So this represents what we call a phase transition in the early universe. Okay, and then we continue to basically form stars forming galaxies, and the galaxies basically kind of continue to grow and evolve, and I'll say a little bit more about that in a second. So to illustrate all that, I want to show you a simulation. This is what we call a cosmological simulation. So it's like a universe, but it's actually it's much smaller than our observed universe, and obviously it doesn't incorporate all of the physics in the universe. This is because the amount of compute hours to run such a simulation already in the realm of tens or hundreds of millions of CPU hours. It would be very infeasible to continue scaling this up. So as always, there's the trade-off between how much compute you put in, the resolution of the simulation, and how big the cosmological volume is. Okay, but this is a cosmological volume. I just want to orient you first. So in this main panel here, this shows the gas, basically this hydrogen, mostly hydrogen gas that I was describing. Down here, actually, you get a perspective of dark matter. I'm not going to say anything about dark matter, except that it constitutes about 80% of the mass in the universe. So it's the majority of the mass in the universe. And as such, it only interacts, as we know, gravitationally. So that means that it sets the backbone of where cosmic structure ends up landing, right? All the other gas, which is the minority, wants to go and sit on where the dark matter has carved out, the gravitational potential, and it sits in those wells. If you're used to thinking about lost landscapes, I make this analogy a lot. Lost landscapes to me are often like gravitational potentials, and I just like to think about trajectories of things, and they want to go and settle in, in where the dark matter wells are, just as your optimizer wants to find its way into the bottom of a lost landscape when performing some sort of optimization problem. And okay, so that's the dark matter. No more about that. Don't ask me any questions. Stars on the right side there is showing where gas is able to condense enough and undergo nuclear fusion, and then gives off starlight. So that's what's being shown in that panel there. Okay, so those are the three main panels, and we're going to go and run with this movie now. So at early times of the universe, this galaxy is trying to be born out of basically just a bunch of gas clouds. And you can see that there's actually a lot of structure on very large scales here in the dark matter, right? So what's happening is that this cosmic web is forming, kind of filamentary-like structure is forming in 3 dimensions, although it's just projected in 2. And you can see the gas is also spiraling in. Now, the interesting thing about gas is it's dissipative, right? So it can actually lose energy and shed angular momentum, causing it to form into these smaller scale structures. A lot of interesting fine-grained structure in there. And indeed, down here, you can see the stars, and actually a zoom in as well of the gas is showing like where it's being born. So in these lower 2 panels. Okay, so this gas is now kind of falling in, and right now we're at redshift 1.7. So this is about 10 billion or 9 billion years ago. So only about 3 or 4 billion years after the Big Bang. And we can see the animation has frozen now, and you can see actually that this galaxy has started to form something that looks like a disk. Let me pause, in fact, and say that, so this actually kind of resembles a galaxy, what we call high redshift or a very, very distant galaxy. Galaxies in the early universe look a little bit different than what they look like today. Kind of the everyday spiral galaxies you might imagine for the Milky Way or our neighbor, Andromeda galaxy. A lot of the early universe galaxies are much more tattered looking. And this is because they take a long time to get organized. Gravity is still causing all this other structure kind of in this clumpy, locations. It's constantly being merged in with other galaxies, things like that. And as such, it takes on this kind of messy morphology. So sometimes people call this the epoch of disk formation, where a lot of galaxies are actually starting to really form disks or spiral arms, right? They're kind of flattening into the characteristic two-dimensional shapes. Let me go back and just kind of go through this again. And as you can see, there's kind of like this planar like structure down here. And in fact, this galaxy is starting to form a disk. You'll see later on through the simulation that it actually does form a disk. Okay, so what's going on with this other color scheme here? This is actually this purple and yellow colors is showing what we call the metallicity, the chemical abundance of heavy elements in this galaxy. So the yellow colors are where there's more heavier elements created by those stars. This now in red and white is showing the velocity structure of the gas. A lot of gas is falling in, a lot of gas is being blown out. And the reason it's being blown out is actually because there is both accretion onto a central supermassive black hole of that galaxy, which is causing basically a huge heating of gas within the galaxy. So you can kind of see, imagine in the middle of this galaxy, there's going to be a supermassive black hole. It causes accretion, which basically you can think of almost like the friction forces, as well as other kinds of forces, which are causing a lot of energy to go and being imparted on its surroundings. And they blast out, all the gas and cause it to go outward, as well as when stars are being born in the galaxy, they tend to form in clumps and then they explode at the end of their lives. So when stars explode, sometimes, we call that supernova. That also causes an immense amount of energy to be ejected outward. And so all those forces are basically causing, gravity is causing the galaxy to want to form new stars, and the central supermassive black hole, as well as the winds from the stars and the supernova explosions are causing the gas to want to go away from all this. So it's kind of a detailed balance problem. And as you see, eventually gravity often wins out, at least in this case, for this massive enough galaxy. You can see that it is really starting to take on, a more distinct spiral galaxy morphology. It actually may be even forming kind of like a bar in the central regions there. And you can see that, some of its neighbors have already all coalesced in. And now, I think this is actually just the gas here. You can see that it's in a pretty sort of stable configuration with no more neighbors around it. Okay, so that's kind of a highlight of, how galaxies are born. So I think a lot about galaxies, by the way, because that's actually the area of research that I mainly specialize in. So I'm interested in how do galaxies form, how do they grow over time, and what can we learn about them, based on things like their appearances, based on how they cluster with other structures in the universe by using things like, geometric learning and stuff like that. So I'm always happy to talk more about that maybe after this. So that is one sort of common thing that you'll see in astronomy. Here, oops, get past this, skip this video. Another thing I want to show is something called an HR diagram. This is known as the most famous plot in astronomy. It's the most common plot that you'll see in astronomy, okay? By plot, I just mean it's a figure with, oftentimes two axes. So what is the HR diagram, the Hertzsprung-Russell diagram? This describes how stars are, basically form and evolve, where they evolve in a observed space. Observed parameter space, okay? So imagine you have a bunch of stars, which are imaged by a telescope like the Hubble Space Telescope. It actually looks something like this. So this is actually a cluster, a globular cluster of stars. So all these pinpricks of light that you see here are just stars, okay? And in this field of view, you have some that are blue, some that are red, some that are more luminous, and some that are less luminous. And so if you now rearrange all these stars by their colors, you can quantify the color by just thinking about the difference in, how much light is in a blue channel versus in a red channel. So that's kind of like a quantitative color. Astronomers use that a lot. And then you also order them by their luminosity. Or really, in this case, it's their flux. But since they're all based at the same distance, the flux and the luminosity are comparable, you actually end up with this kind of characteristic shape. So this is the HR diagram in a space of luminosity versus color. Main sequence stars are shown here. So by main sequence, we basically mean, So main sequence is basically this big sequence of stars right here from the lowest mass stars. Low mass stars have less gravity, basically are less able to form, very, very hot, they're less able to basically fuse very, very heavy elements. And they also burn sort of at a cooler temperature. And so redder colors often indicate cooler temperatures. And then bluer colors often indicate hotter temperatures. And so what's happening here is that actually sort of along the sequence, you're kind of marching up in the mass of the stars. So they're becoming more luminous. Oh, crap. They're becoming more luminous, and they're also becoming more blue, or kind of white, intermediate here, along the main sequence. There's also this sort of branch over to the upper right that you see there. That's the red giant stars. And then you can also see the horizontal, the blue horizontal branch stars. So these are sort of different stages of stellar evolution. There's even white dwarfs kind of in this little corner here, but they're also very, very faint. So that's called an HR diagram. Again, a very common figure that you'll see in astronomy, probably known as the most famous plot in astronomy. So at this point, I want to make a distinction. Basically, just thinking about astronomy, the way that we think about physics, we think about statistical inference and learn about the universe is kind of different in astronomy than in some other types of fields. The reasons are, there's a lot of reasons. One is that there's only one universe to observe. You can't really change our position in the universe, so we can't even really get multiple perspectives of it. We essentially are always just sitting, in our solar system, in our galaxy, looking through a dust-shrouded, region that we live in, and we look at the one and only universe that's around us. And then we try to say, I wonder what are the physics or the parameters that govern this universe. Now, for that reason, I think the way that we do statistics is also a little distinct. And I'm going to say a little bit about that more in the second part of this lecture. But one of the things I want to highlight is that we often have an observed parameter space and we often have a physical parameter space. So in this case, this observed parameter space, I'm just grabbing a bunch of galaxy image cutouts and I'm arranging them by their luminosity, basically how bright they are, right? How much integrated light they have over all the pixels here. And then also whether they're bluer or redder. Again, this very similar to the plot that I just showed, the HR diagram, which is the same thing, luminosity versus color. Except in this case, I'm now showing galaxies. So even though these things look like this, and oftentimes we can draw some, toy distributions that look something like this. You have a cloud of sort of bluer points, which are these bluer galaxies, and then you have what's called a red sequence of galaxies that represent sort of late stage galaxies, galaxies that have evolved over time. They become redder. But interestingly enough, when you actually map this onto a physical parameter space, you actually have a kind of a big cloud of potentially quiescent galaxies, galaxies that are not forming stars at a high rate versus their mass. And so the mass is kind of proportional to the luminosity. You can think of that as like a galaxy with more mass tends to radiate more light. But the star formation rate is this other key parameter of galaxies, which is like how quickly am I forming new stars? And that star formation rate kind of maps onto this observed parameter space in a sort of a opposite way. So redder galaxies often indicate low star formation rates. Bluer galaxies, will have higher star formation rates. And the reason for this is because when you form stars, there's a bunch of high mass stars, there's a bunch of low mass stars. The high mass stars will tend to die very quickly. They burn through all their fuel, they live fast, and then they blow themselves up in timescales of just about 1 million years. Very, very short on the astronomical timescale front. Meanwhile, the very low mass stars can live something like 1 trillion years, right? So they can continue to outlive all their hot and bluer colored massive star counterparts. So once you form some stars and you stop forming stars, what happens is all the blue sort of massive stars die away, and all you're left with is the redder colored stars. Yep, question? I mentioned what? I'm sorry? Yeah, million years. Few million years. Yeah. Like our years. Yeah, that's right. A few million years. That's in.
Saying trillion.
Trillion years. Yes. Trillion years.
How long has?
Yeah. So okay. Right. Right. Good question. I said 1 trillion years. Yeah. Good catch. So the universe is 13.8 billion years old. There are lots of lines of evidence that support that. When I say that some of these low mass stars can burn for trillions of years, this is a model expectation. So we understand the physics, to some extent of how, these stars are continuing to evolve. And, if they basically are just burning hydrogen, that is fusing hydrogen into helium at a very, very slow pace, then they will be able to sit around and just continue doing that for essentially 1 trillion years. Like they could, and some stars, some very low mass stars can just basically sit around and do that for the entirety rest of the universe. Not very interesting. Does that answer your question? Yeah. Yeah, so just to be clear, they're not currently 1 trillion years old. We expect that they will live 1 trillion years or so, and they will outlive all of their blue stars. And so eventually, if a galaxy stops forming stars, it will basically kind of fall down into this quiescent part of this plot. And so oftentimes, as you see galaxies, what do they do? They actually hop around. They sort of rise up onto this star-forming sequence of where galaxies are kind of growing. And then they every now and then, once they lose, enough gas, they basically fall into this quiescent pool. The confusing thing, though, is that when we observe them, they're in this color sort of luminosity space, and it's actually really hard to untangle this kind of pileup of things that are in this redder space. That is, there's this red sequence of galaxies, but galaxies basically, they can't be arbitrarily red. They eventually just only have old stars, and we call these red and dead galaxies. But they can basically, have this non-trivial mapping between the observed parameters and the physical parameters. That's all I'm trying to make here. That's the only point I'm trying to make with that. Yes.
And a chart diagram when they go from the
In a sense. So yeah, so it's actually kind of contentious. This, like, for instance, this kind of thin correlation of where galaxies often live up there, and I wrote star-forming galaxies. Some people call this a main sequence of galaxy formation, but it's not the same way. It's not the same type of sequence in the same sense that the HR diagram, like all the stars, they always live right on that line. Whereas in this case, there's actually a lot of different covariates that we have to account for. And they often will fall off of this line. They will scatter in and scatter off. This is more like an attractor solution in in kind of like a dynamical system. Yeah, exactly. Yep. Yeah, thanks for that. Any other questions? I know I'm like covering all of extragalactic and stellar and whatever astronomy. Yes.
It's not what it is, right?
Yeah.
We need to extrapolate, right?
Yeah, we can extrapolate.
How do you do the curve?
How do I know what?
Like the shape of
The
the
curve.
extrapolation
The
curve.
shape of the extrapolation, yeah.
Oh, yeah.
It's like, if you see like
Mhm.
10 years,
Yeah.
it's going to live for 80 years.
Yeah. So in a lot of stars, we actually understand the physics quite well. It's because, what they're doing is they're really just collections, like in the simplest sense. Let's say you have a very low mass star in the early universe. All it does is it just has a bunch of hydrogen atoms and you put them all together, right? So that hydrogen becomes now a kind of a plasma of protons. There's a lot of electrons that are flying around and whatnot. And within there, now interesting things can happen, I'll say that. But, in general, what all you're doing is turning that hydrogen into helium. And you're continuing to, there's basically a cycle of nuclear fusion that can happen in there. And at some point, especially with these very low mass stars, they cannot burn heavier elements because the amount of gravity that they need in order to get like two helium atoms to collide is actually, significantly more than to get two hydrogen atoms to basically fuse together. So this is kind of getting into the nitty-gritty details of stellar nucleosynthesis and nuclear fusion and so on. But what the point is, though, like actually at its core process, if you don't take into account like annoying effects like convection and certain things, which we know exist in certain stars, the atmospheres of certain stars, but for many stars we can model reasonably well, or at least we understand exactly what physics are at play here, we can actually just say like, oh, this thing enters essentially a steady state fusion kind of thing, and it's just continuing to do that. And we expect that it will continue to do that for 1 trillion years because all it has is just a pile of hydrogen to burn. Does that make sense? Yeah. Oftentimes, and this is kind of an interesting point, actually, I should say, is that in our terrestrial, our world that we interact with, there's a lot of different modalities, right? So we look at things like here, this is, a backpack, and here's a cup of tea, and here's a laptop, and these things are very, very different. In physics, you actually have many fewer things to play with, right? This sort of lack of modalities, you have things like galaxies. Galaxies are, spiral, sometimes they're elliptical, but they're kind of all just galaxies. They actually undergo many of the same physical processes. And so the way that we think about these kinds of problems is often quite different than the way that we think about, tackling problems in, say, machine learning as a whole, computer vision, et cetera. And so I think as such, we also need to be careful with, what kinds of priors we're putting into these problems. So in physics, because we understand that we understand much of the laws of physics, we can use that to constrain the way that we think about and solve different problems. Any other questions? Yep.
So, astronomy, what are the current questions?
In all of astronomy, what are the goals? There are many. Yeah, there are many. I think there are a bunch of core goals that I'm not really going to touch upon. There are sort of like the big questions of like, what is the nature of dark matter? What is the nature of the expansion of the universe and its current accelerating pace? There are questions about what happened in the very, very early times in the universe. Like, for instance, can we start to understand things before the surface of last scattering? There are sort of methods of doing that. And then there are other more complex questions, things like galaxies are, there's actually a lot of physical processes that we expect are determining how they grow and evolve. Can we actually understand all of them and see which ones are sort of most prevalent, right? A galaxy, as I mentioned, is kind of this competing, it's growing due to the competition between, it's constantly trying to blow itself apart, and its gravity is trying to fuel, new additional formation of stars. And this is actually this makes it a very sensitive problem to a lot of different types of physics. So do we understand the physics, well enough to be able to model those kinds of things? And then there are always the more unknown unknowns. There are a lot of like things that we just simply don't even know where to start looking. People who are interested in exoplanets want to look for signatures of life on planets or moons or whatever, things around other stars. So that's another sort of active area of research. And so these are all very big questions. I would say that right now we're on the frontier of having AI-assisted discoveries in different ways. I'll say more about that later. And we're also coming up on an age where there's a lot of new telescopes that are coming online. So instruments are getting kind of more powerful, and that often will fuel another wave of discovery. So I think some of it will just be an idea of like creativity will let us kind of determine what are the problems that we can solve, given the new instruments or the new telescopes that become available. Yeah, thanks for that. Any other questions? Really, anything goes. Yeah.
Talk about James Webb later.
A little bit. I'll actually, in the second half, I'm going to mention a little bit about Space Telescope Science Institute and its role.
I meant more maybe on the impact of the current theories of formations of galaxies and so on, which the observation, as I understand it from amateur perspective, somehow challenges the current models of formation of galaxies and so on. So
I'll say this. So the James Webb Space Telescope can see in the infrared wavelengths, and because again the universe is expanding and things are receding away from us, that means that light that was emitted at the time in the ultraviolet or the optical or whatever actually gets redshifted, it gets stretched out into the infrared. And so we can start to see those now with the James Webb Space Telescope, or JWST. We are always learning new things whenever we learn in a new region of observational parameter space. Basically, every time we look somewhere new, we find new stuff. So I would say that it is true that there are interesting new challenges that have appeared. For instance, we are finding accreting supermassive black holes all over the place at far more, basically more than we expected, or at least more than we know how to model physically. But actually, in fact, it actually partly solves the problem, because we actually know that all galaxies have these very, very massive black holes in the centers, and we actually don't know how they got so massive. So the fact that we're finding them is an interesting, support of the observational evidence that those supermassive black holes exist, but we're not really sure how to cause them to get to such a high mass so early in the universe. There are things like that.
It's, because I've heard it, but it's just the popular opinion. I think that it might challenge the age of the universe more dramatically than just a statistical, let's say.
Yeah. So the question about challenging the age of the universe. I'll say that probably 99% of professional astronomers do not think that it poses any challenge to the age of the universe. There are certain things that make for really interesting news items or press releases, and that's definitely one of them. It's kind of a complex topic, right? But I don't think that it really causes or necessitates a revision of our theory of cosmology. So oftentimes what happens is cosmology. Okay, so there's actually, let me just say one more thing. The interplay of cosmology, the study of the universe at large, is basically to say, let's write down an elegant, 6-parameter sort of model that just tells you everything about the universe. In order to do so, and if you do the statistics, you just say, oh, but there's all these other things we don't understand about how, like the messy, stellar astrophysics and galaxy astrophysics and the microphysics of very low density gas, like things like that, which matter because they tell us what we're actually looking at in the early universe in order to make inferences about cosmology. But oftentimes in cosmology, you need to marginalize over those parameters, right? You basically say, there's a bunch of messy astrophysics in here. I'm just going to assume that I can just marginalize over them, that I've sort of sampled the space in a statistical sense. And whatever parameters I've assumed for those, that those are good enough. And those models, like I've covered the full space of those models, and then we're just going to pretend they don't exist anymore. So they're all nuisance parameters. Basically, the joke is that to a cosmologist, all of galaxies and stars and everything are just nuisance parameters, things to be marginalized away. That definitely makes it easier to write down an elegant model, but you also, in some sense, you have to really be sure that your model parameters are correct. And oftentimes what happens is if you take an age of the universe and you say, oh, well, we understand all of galaxy astrophysics, but in fact, we have a systematic discrepancy, right? If galaxies are fundamentally, let's just say they give off more red or light than we ever thought they did because of something, then failing to account for that will cause major shifts or major biases in the way that we do parameter inference in cosmology. So I know I'm like jumping in and out of like very detailed in the weeds to like kind of big picture stuff. So again, I'm always happy to chat about this more at length, just on a more casual front as well. Any other questions then? All right. Good. I want to talk a little bit about what we mean by multimodal data for astronomy, because in astronomy, there are different types of data sets. Honestly, the ones that I'm most familiar with, and oftentimes what most people think about, are just these images that you see in the background here, where you just survey the entire sky, okay? But there's a lot more to that, and even from images like these, you want to extract different types of information. Okay, so by the way, this is from something called the Legacy survey, or it's actually the Dark Energy Spectroscopic Instrument Legacy Imaging Surveys. But we all call it just the Legacy Survey. If you go to this URL, legacysurvey.org/viewer, you can actually kind of pan around in this, basically this map of the sky taken with this world-class telescope from Chile. Actually, it's a set of telescopes in the northern and southern hemispheres. And you can look at like images like this all day. It's actually a lot of fun. I set it to my homepage because it actually kind of it randomly selects like a galaxy to hone in on. Okay, so looking at images like this, you can actually extract a lot of information. And so now I've kind of panned to, actually this is one of my favorite galaxies. This is called NGC 3044. It's a lot of fun. This is a galaxy kind of like our Milky Way, but also it's got these two little companions. I don't know if you can see them. There's one here, very faint fuzzy blob to the sort of lower left. And then there's another one that's right over here. Okay. So I actually spent a lot of my time studying these, they're called dwarf galaxies or low mass galaxies, because they're really sensitive to all kinds of different physics. Like it's really hard to form these in our simulations properly. Because if you add just a little too much of like one type of physics, you like absolutely like destroy them all. And if you do another type of thing, you absolutely make them way too big or something. You can mess with their properties dramatically because they're very small and therefore sensitive to a lot of different types of physics. So getting a good census of these things is actually a major another major outstanding problem in astronomy, to get an unbiased and statistical understanding of how these low mass galaxy populations are around. So imagine you want to go and study, different types of data in astronomical imaging. Well, one of the big problems you need to do is astronomical segmentation of these images, right? And so by segmentation, I just mean basically finding all the things that are out there. This is sometimes easy, sometimes really, really hard. In this case, it's not too bad, as you can see. Like this is pretty faint, but you can see by eye that it's there, which means that you can probably do this algorithmically. Obviously, there are a bunch of other things going on. There are stars in this image. There are, other galaxies in this image. And in fact, covering the whole entire sky, you have right now, tens of billions of objects that basically, have to be somehow segmented. And not only segmented, but also sort of de-blended from each other. Sometimes they're overlapping, okay? And oftentimes you also want to take that and model what we call the photometry. This is basically like taking inventory of the light in the system. So what will happen is you actually basically draw some, let's say like a two-dimensional Gaussian model that just shows like this is what the light distribution kind of looks like spatially. And you do that for every single pinprick of light, right? So maybe a couple thousand in this image, but again, billions over the entire sky that's visible. And you draw all these like tiny little like, small Gaussians of where the light is, or, and then you can look at what the model is and what your original data look like. You can even, just for good measure, take a look at the residuals and subtract the two to make sure that you're getting a good fit. This, again, works well for things that are pretty simple, like this galaxy here. You can imagine that if you try to model this giant galaxy up here, that would be a lot messier to do because you can't make a very, very simple model for it. And in fact, you have to come up with lots of model components. There are other things that can happen. Like if you've seen images like various nebulae and whatnot that are shown by the Hubble Space Telescope, right? These have a lot more messy appearances. You have things that look like, like these kind of weird cliff filamentary like structures and all sorts of other stuff. Those are also much harder to measure, to catalog, and also really hard to basically to segment, right? It's kind of unclear what is a thing, at that point. When you talk about things like the interstellar medium, this is interstellar gas filaments and dust and things like that. Like what even is, a cloud? It's kind of all interconnected in this filamentary structure. So obviously this is kind of a challenging problem. But let's say that we can not only segment the sky, but we can also model the sky. Then what we can do is take our model, if we assume that this is a sort of a denoised version of the sky, if we've done a good job of it, we can then construct catalogs or tables of all of the parameters that went into this model, right? Things like, what are, you basically have to keep track of everything, right? Like where's the position of this thing? What is its shape parameters? How much total light does it have? But also like things like when was this observed? Did we co-add images from multiple epochs? Because maybe one night that it was observed, it was a little cloudier in Chile on that day, and maybe sometimes the telescope was at a slightly different orientation, or maybe a SpaceX Starlink satellite went through the image, and so you had to reject a few of them. And like that information needs to be cataloged and put together into this kind of thing. So then you have this billion to 10 billion rows in your table. You have like hundreds to thousands of columns in your catalog or your table here. And so this is the kind of data set that oftentimes we start to work with. But this is assuming that we've already thrown away the imaging, right? This is just reducing the data into its most simple form that we think, assuming that a model works well. We also, of course, have the pixel scale information, right? And this is sort of at the petapixel scale, I think, if you look at all the pixels in the universe. Yep.
Does that get featured and so on, or is it something that matches like AI?
Yeah, so it's automatic. It's not usually done with AI right now. Generally, what happens is that, as you can see, so right now, this is sort of the easy regime. Most of these things are not overlapping with each other, which means that you can sort of model them independently and quickly scan, right? You can do an iterative process. There are a lot of different algorithms that people have designed, which have been used for, at this point, decades, and we're constantly getting better at them. Now, when things start to get tricky is actually as we get more and more sensitive telescopes, you end up being able to see, deeper. Basically, you can see more and more stuff. And actually, I'm going to show kind of an illustrative example of that in a bit. And when that happens, you actually end up having to basically jointly fit a whole bunch of different things. And in fact, if you have really good vision, you can actually see that there's in this galaxy, there's actually like a little blip of light right there, which gets neglected. It's not in this model. And so when you go to the residual, it's like showing up over there. I don't know if you guys can see that. So that's an example. Yeah. So that's an example of when, your model is failing a little bit, right? Just because the segmentation didn't catch that little, it wasn't able to find that little peak in the light distribution. And so maybe this is where we can use more like computer vision like techniques or AI or something, to really do a better job of this. but the jury is still out. There's like, this is definitely an outstanding problem, and you want to be able to do this at scale, right? Like you want to be able to do this for tens of billions of things. And so running, really expensive AI like, model is probably not probably not feasible right now. Yep.
Area where you study.
Is there any connection? Well, I did jointly supervise a student with somebody who works in medical imaging this past semester. And so some of the techniques do overlap. But one big difference, well, there's several big differences, right? But one is that actually like the sky is very sparse, right? Most of the pixels here are black. Now that will continue to change as we get more and more sensitive sensitive telescopes that can see deeper into the sky. But for that reason, there's actually a lot of you basically have to get things that are really efficient at finding rare, faint things. Oftentimes, the frontier of our understanding of astrophysics is pushed by the faintest, rarest objects, because those are the things we didn't account for in our theories. The other thing is that there are rarely correlations over very, very large scales. So techniques like convolutional neural networks with small kernels actually work reasonably well in our field, maybe in a way that in medical imaging you might not expect, because you might expect more global sort of connections, things that like a transformer model or some other sort of thing would work well. So for instance, like my inductive bias, I don't know if you guys are familiar with the term, but my inductive bias is basically based on the nature of our data, is that things like vision transformers are ill-suited for astronomy, and that's because you're sort of losing out on the fact that you don't expect there to be very long range correlations. These are like so far apart that and not only are they really far apart, they're also at different distances from us. You're seeing them all in projection on the sky. And so the nature of the problem is a little bit different, but there are things that we can learn for sure. I hope that answers your question. Yeah, you're welcome. Anything else? Okay, let's see where we're at. Oh yeah, good. So this is sort of the state of the art of astronomical imaging. This is just really on a random patch of sky, circa 2000, turn of the millennium. Okay, so this is something called the Sloan Digital Sky Survey, probably one of the most impactful wide area surveys. The first time at very, very large scale when the sky was digitized and not just kind of recorded on photographic plates, therefore on pixels, could be archived very well. And also, it was sort of cross-matched between this data set and a couple of other data sets that really made it very valuable for all sorts of general science. This is really like, you can think of this as almost the birth of like large-scale big data in astronomy. So this is just one tiny patch of the sky. I've zoomed in like dramatically. I really can't emphasize this enough, right? I've zoomed in on just a random total patch of sky. And obviously, if you zoom out, you'll see tons and tons of stars and galaxies and structure. But even in this image, you can see a couple of galaxies, a couple of stars, perhaps, if you're able to recognize. The galaxies are the things that are just more extended. They're bigger. Okay, but this is, and in fact, a lot of machine learning papers were written with this kind of data. Yeah, what's up? Yes, good. So this red, green, and blue sort of pattern is just noise. Yeah, so that's mostly shot noise. So Poisson distributed noise. Yep. And you'll see, so if we sort of advance about 15 years, this is from the legacy survey, basically what I just showed before. So kind of, and this started, in earnest about 10 years ago. So you can see, sort of just flipping between the two, that galaxies are starting to take on more of a resolved appearance. That is, you can see more structure in them. You can see in the background things are actually popping out of this noise, out of this speckled noise that you see there. And there's just there are more images and there's a lot more structure that you can see in here. And then if you fast forward a little more, there's something called the Hyper Supreme Cam survey, which is actually very similar to an upcoming astronomical survey that's going to begin next year. Basically one of the biggest efforts by the United States ground-based astronomy program, which is called the Rubin Observatory. The Rubin Observatory is basically, it's going to start taking images that look a lot like this next year. And so now kind of going back, sorry, there's a bit of a lag here. You can actually, again, start to see that there's more structure. There's a lot more objects that are popping out of the background. kind of like these little bluer blips in the background. Wow, there's really serious lag here. And what that's doing is allowing us to go even fainter and see a lot more galaxies. Basically, all these little blue things here, they're all galaxies, like very distant galaxies, right? They're kind of all over the sky. And then finally, this is what the Hubble Space Telescope sees. And it's actually kind of comparable to what we're going to start to see across very, very wide fields of sky with what's called the Roman Space Telescope. The Roman Space Telescope is sort of NASA's next flagship mission, which is going to be operated, at least the science operations are going to be done out of Space Telescope Science Institute. I actually work on the Roman team, so this is very near and dear to my heart. But this will allow us to basically get something that looks like the Hubble Space Telescope imaging. You can see in this case already, many, many thousands of images, a far cry from, or thousands of galaxies, far cry from what we were seeing before with the Sloan Digital Sky Survey. Right, this is the same exact field, right? And when you go to Roman-like imaging, Nancy Grace Roman Space Telescope, you can see that all of these structures are starting to be resolved. Like this galaxy before was just a green blip, and now you can see that it's got, it's kind of got this spiral arm that's being tidally stripped or flung around. You can see probably that's interacting with that galaxy up there. There are galaxies all over this image, and if you actually see this on a screen, there's many, many more, right? And so what this really means is that there's sort of a vast discovery space in astronomy that's awaiting us. I think, just there was the question about what are sort of the big questions to be answered, but I think a lot of it's just going to come down to the fact that we're going to see so much more data than ever before. And this is, again, just on the imaging side. Yep. Yeah. So the colors that you're seeing there, yeah, you're going to want to zoom in much more, but it's kind of complicated. They're taken with different telescopes. There's a lot of sort of 0-point calculations of like how do you calibrate these very precisely, but over very large pieces of the sky, and also accounting for the fact that things like there's dust in our own galaxy, which has different amounts, in different parts of the galaxy, and you're peering through dust, which selectively reddens or makes, the colors different of the night sky. So and then there's zodiacal light, there's, instrumental characteristics of the observatory. So there's a lot of different things going on in that particular image. Oh, in the image here? Yeah, so okay, so what's happening here? Why are these slightly changing in color? It's because they actually have different, they're being seen at different wavelengths. And so these are all false color images, right? None of these really are equivalent to the human visual cortex. These are all done using, basically some sort of, we call them bands, or basically like wavelength ranges that are seen by a telescope. Yep. Yeah, so Roman is going to go from the visible or the optical wavelengths to the near infrared. So it's going to be quite similar. It's going to go a little farther out into the infrared compared to Hubble. It's not going to be able to do the ultraviolet, which Hubble can do. But yet the next generation one actually will be like able to do that. That's called the Habitable Worlds Observatory. And then and it's not quite like JWST either, James Webb, because Webb is going to kind of go all the way into the mid-infrared. And Roman can't quite do that. Yep. So really what it is it's going to be able to survey the night sky at sort of unprecedented detail and speed. Hubble can only basically, you can think of it as it can just zoom in on like a tiny bit of the sky and look at that. And Hubble will be able, and Roman will be able to cover everything that Hubble has ever looked at, in terms of sky area in maybe just a couple of weeks. Hubble has been around for 34 years. Right. Hubble has been around for a long time, and so Roman is just about 1,000 times faster in surveying the night sky. Okay, good. Other modes of modalities, right? So spectra are very important in physics, in physics and astronomy. And in fact, just fun fact: the difference between astronomy and astrophysics, according to the American Astronomical Society, is that whenever you take a spectrum of something, that should belong in the astrophysical journal. That's what this is what our community guidelines basically came up with back at the, in the early 1900s. They created this journal called the Astrophysical Journal, which is different than the Astronomical Journal. And the distinction that they made was there was this newfangled people taking spectra of astronomical objects. And they said, oh, no, that's physics. So when you take a spectra of things, now you're really looking at physics. Okay, so what are the physics here? So let's say you take all the light in this this galaxy here, and you disperse it over, let's say, like something like a prism, but something where you're able to separate the different components of light at different wavelengths. Okay, it's not usually a prism, in actual observatories, but you can think of it as something similar. And what you see is this characteristic fingerprint of all of the content in that galaxy, all of the hydrogen and the helium and the whatever other elements, the oxygen and iron and so on in that galaxy, and it basically gives you different intensities at different wavelengths of light. That's what a spectrum is. And so maybe it glows very specifically at what we call spectral lines at these very particular intervals. That is dictated by quantum mechanics. And so again, this is a very specific fingerprint that we can use to understand galaxies. So this is just another example of spectrum. This is how we really know that these galaxies are that distant away. Without spectra, we wouldn't be able to tell, like how far these lines have been redshifted. As I said, due to quantum mechanics, we know exactly what wavelengths each of these spectral features should be at. And so when we see that they've all shifted, together in unison to a different part of the spectrum, we can precisely say, this is the redshift of the galaxy. Therefore, this is what the cosmological distance is. All right, you can also take, I'll just quickly say, you could take the spectrum of every single pixel, in an image. So this is sometimes called hyperspectral imaging, I think. In our field, we call it integral field spectroscopy. Basically, this is really helpful for getting, the spectrum. Again, you can characterize the physics at almost every single pixel of something that's emitting light. Okay, and I don't want to neglect, even though I know nothing about it, time series. So the transient universe, it turns out that the parts of the universe do evolve very quickly in time. So when supernova go off, that is when a star explodes at the end of its life, it gives off a huge amount of light. In fact, it can outshine its entire host galaxy for a brief period of time. This is a different type of transient event. This is gravitational waves, something that's only become possible very recently and has won the Nobel Prize. When I started my career in astronomy, this was still, we didn't know how far away this was. Probably we were thinking maybe decades away because we hadn't seen anything after 20, 30 years of monitoring. But in this case, this is something detected in 2017. This is actually a kilonova. Basically, you can have the merger of very heavy objects, things like two black holes, or you can have a black hole and a neutron star, or maybe even two neutron stars, which I think in this case, that's what happened. And so this is showing the intensity of not light, but actually of gravitational waves as a function of frequency and the time. Okay, so this is kind of like a spectrogram, right? But you're doing this for gravitational waves. You're not doing this for, any sort of like not audio waves or anything else. Okay, so this is another way you can kind of study the universe. You can try to monitor for these sorts of things with very, very, very precise instruments. And in fact, that gravitational wave was accompanied by this also appearance of this little guy right here, and that is the kilonova shown in the electromagnetic spectrum. So this was seen in not just gravitational waves, but also electromagnetic waves. I think we also pointed to a neutrino telescope to go look at that, and I believe some were detected. But you can basically actually characterize, astronomical transient phenomena with all kinds of different types of detectors. So this is all time series data. Now, you might also be more familiar with the search for exoplanets. These are planets around other stars. This is a very hot topic now. And the way you often look for these, at least in certain types, in this kind of analysis, is by monitoring a star for a very long time. And sometimes what you'll see is that there will be dips, in the amount of intensity of light coming from that star. And that's actually what happens when your extrasolar planet or exoplanet passes in front of the star and it blocks, a tiny fraction of the light. And so you actually see these periodic blips when the planet passes in front of the star, right? So this is these are called, this is called transits. When the exoplanet kind of passes in front of the star and you're looking at it, and all you're seeing is kind of the shadow of that blip. So the relative intensity is, in this case, 99% of the flux of the star. Sometimes it can be in the, parts per thousands or even parts per millions in terms of the difference in flux. And then if you take that and detrend, you basically wrap around the phase or the periodicity. If you estimate what the period is, then you can actually go and create a transit curve that looks like this. This is now the phase wrapped transits. You can put that in hours, in fact, and you can actually start to characterize things like the size of that planet relative to the size of the star and other types of interesting studies. So I don't work in exoplanets or in, astronomical transits, but a lot of folks do in the area. So, there's a lot of interesting stuff being done there. Okay. Oh boy. Okay. Statistics and astronomy. So we've had a storied relationship with statistics in astronomy, and that's actually because very early on, astronomy is actually known as the oldest of the natural sciences or the physical sciences. This is partly because, everybody has access to the night sky, at least back in the day. You can all look up, and people are very interested in understanding celestial bodies and how they either moved around or how they stayed put or how bright they were. This was useful for navigation. This was useful for conning political leaders with astrology. It had all sorts of great uses way back in the day. But right now, even as early as the 4th century BCE with Hipparchus, statistical techniques were developed for accurately combining measurements, either made by different people or, people from different locations on Earth who basically reported, oh, I saw these kinds of signals. Like people have reported the detection of supernova, even very, very early on. And so statistical techniques, I'm not going to go through all this. I actually kind of stole this slide from one of the pioneers of astrostatistics, Babu. You can see the citation there. But basically over the past, past 5 or 6 centuries, a lot of statistics was developed in order to better understand astronomy. Now, actually, after about 1900, it was really recognized that statistics would be extremely valuable for other things other than astronomy, things like making money, so economics, things like, I don't know if you know, Students' Tea Test was founded by the head brewer of Guinness to ensure that they could brew beer very reliably, even if they take, draw random samples. And a lot of different, developments in statistics took off there in order, for different range of tasks. But, back in the day, though, a lot of this was driven by astronomy. And it's partly because astronomy has, there's a lot of data. The data have weird biases, and oftentimes you want to try to combine those signals, even though they're somewhat discrepant. They have uncertainties. So these are the only equations I'm going to show in this and the next talk. So please bear with me. I just want to give you a sense of what kinds of annoying things happen, right? This is kind of what you learn at the Astronomy 101 course. Okay, imagine you have some source that's emitting some amount of light. It has an intrinsic luminosity, L, which we're going to just assume is constant for all of these types of sources. And we're not trying to study just this one source in particular, but we're actually trying to understand the population of these sources. So let's say that this kind of source, let's just say it's a star, okay? This star always has luminosity given by L, that's constant. Now, if you see that this star is at some distance from you, R, then you know that the amount of flux that radiates upon your detector or your eyeball or whatever is given by F, which is equal to L divided by 4 pi r squared. This sort of 1 over r squared relationship is characteristic of basically the apparent flux that is coming out of a system of a luminosity L. Okay, so what we can say then is r is proportional to 1 over the square root of f, or f to the minus 1/2. But now if you take an assumption that you want to count up the number of objects within this known volume, which is sort of bounded by r cubed, or bounded by r, so you're drawing now a sphere out, and you also assume that you have a uniform distribution of these sources, so n naught, which is the number density of objects, is constant. Then what you end up with is n is proportional to r cubed, right, and nothing else, and then n therefore now is proportional to the flux to the minus 3/2 power. So something that you know to be uniformly distributed in this spherical volume, actually the apparent flux, if you make a cut on flux, if you say I'm only selecting things above a given flux threshold, which is the apparent amount of light that you see, you actually end up with this kind of weird biased distribution of sources, right? Where the differential number counts dn df is going to be f to the minus 5/2. And so this often creeps up in astronomy, and even papers, like you'll see published papers now, they'll fail to account for this all the time, right? And this causes all sorts of like stupid problems, and it's really, it's kind of embarrassing, but it's also just, it's such a pernicious effect that, when we want to study populations of objects, we always want to make sure that we're not being biased. This, of course, makes some assumptions that I just mentioned. F is precisely measured. There's no measurement error. The luminosity has no scatter or very little scatter. And that, again, the sources are homogeneously or isotropically distributed. So just to kind of illustrate that, if you basically have, again, a constant luminosity, in this case now with some scatter at some range of distances, this is what happens if you have a 1 over r cubed sort of volume constant, basically constant distribution, right? So most of the volume is actually out at higher distances, right? This is, again, the assuming a uniform distribution in a sphere. This distance is a radius. And so then the mean sort of point here is given by this sort of purple bar, which shows the mean of all those purple scatter points there. But if you make a detection limit, you know, and you basically say, I'm only going to select things above a given flux, you end up with this kind of weird, you know, angled thing. This is this, basically this is the effect I just mentioned. And what this does is it causes upward bias in your detected objects populations, which now give you the wrong luminosity, right? And so what you actually instead need to do is you need to determine what we call a volume limited sample, not a flux limited sample. Your selection must be as a function of volume, which also basically assumes that you're not trying to study anything with the luminosity lower than, you know, some lower bound. And then you can now create what we call this volume limited sample, where we again try to recover an unbiased estimate of the detected population. So in other words, we're going to throw away all the stuff that's out here in that wedge, because we know that that's a biased sample. This is just like, you know, again, this oftentimes in observational astronomy is something you have to account for. Another thing that often happens is that when you have a number distribution, basically a PDF of objects, this n here, which, you know, number of objects, again, we can think of stars, which are greater than some detected flux as a function of flux. This is sort of a common distribution in astronomy. So if you have a power law distribution, you know, go something like a negative power law, you know, what happens is that if you have a detection limit, you have many more objects sort of on the left side than on the right side, right? So any objects on the left side with a little bit of measurement uncertainty, there's many more things that are likely to scatter into your sample at a constant detection limit than brighter things that will scatter out. Again, this is a kind of a pernicious, seems like a really subtle bias, but it can also cause all sorts of problems in biasing your understanding of populations of things. This is like, again, this keeps a lot of astronomers up at night thinking about like, oh crap, like, did we actually account for all these different types of uncertainties or these biases? Okay, and then I'm just gonna, I have maybe 5 or 10 minutes left, so I'm just gonna quickly now talk about the rapid rise of machine learning, which, as you can see, is quickly outpacing all the statistics in astronomy. And this is, again, because astronomy represents a very big data field. You can see deep learning down there. This is as of 2022. You know, deep learning is rapidly rising, and I don't know, I guess if you put AI or something in here, maybe it's also growing at a similar clip. Okay. This is kind of just this is almost like a brief opinion piece, if you will. You know, a lot of times in astronomy, astronomers spend a lot of time looking at these galaxies and realizing that, there are some interesting heuristics that will help us learn about galaxy physics. So as I said, we learn about galaxy physics by taking spectra of things. We grab spectroscopy of these galaxies. We say, you know, these galaxies' physical properties are correlated with some of their other things that we can get without spectroscopy. Things like their appearances, right? So when I say galaxy morphology, I really just mean their appearances, images like this. And it turns out that, yeah, if you look at galaxies that look like this, they tend to be red and dead, that they haven't had formed new stars in a long time. They tend to have, you know, a surplus of, you know, heavy elements and so on. If you look at galaxies all the way on the right there, those end up being actually pretty young galaxies. They're just starting to form. They often have a lot more primordial hydrogen relative to the heavy elements and other kinds of things, right? And they have different dynamics and stuff, different kinematics, right? The gas and stuff is moving in different ways. All those things, typically you would need spectroscopy to learn. Okay, so Edwin Hubble, you know, back in the 1910s, looked at all these images of galaxies and realized, yes, there is a correlation here that I can latch onto, and made this classification scheme. So ranging from elliptical galaxies, very spheroidal, to, you know, some categorizations, which then now split off into things that look more like galaxies with disks or with spiral arms. So on the upper branch, you've got regular spiral galaxies with sort of gradually sort of outward expanding arms, basically you can see sort of like the I'm forgetting the term now, but like, the spiral, the pitch angle, that's what I'm trying to think of. The pitch angle of the spiral arms is expanding as you go from SA to SB to SC. Okay. And then same thing with spiral galaxies that have bars. Okay. And their morphologies actually do, map on well with their physical properties. But, circa 15 years ago, Chris Lintott and others realized that actually people like looking at images of galaxies. They're really pretty, right? So why don't we get citizen scientists? That is, why don't we just go and crowdsource, this task of classifying galaxy morphologies, which is very time intensive, to, others who might be very interested. So citizen scientists can help us classify that galaxy morphology, which will help us eventually learn about galaxy physics. This is actually super interesting. There's a website now called Zooniverse, which you can volunteer and you can look at things, not just about galaxies, but actually throughout all of sciences. I actually checked yesterday. They even have one on languages and they have some on literature too. But there are basically these usually classification or annotation, data annotation sort of experiments that where volunteers can go ahead and label data for you. You don't have to go and put a bunch of money into Amazon Mechanical Turk or whatever. So Galaxy Zoo was really interesting, and it began 15 years ago, and actually led to a lot of interesting discoveries. For instance, an entire new class of galaxies called green peas were discovered as a result of this. It's a paper from 2009. These green peas are actually really interesting because we actually think that they played a really major part in reionizing the universe, something that happened really, really early in the universe. And James Webb is seeing a lot of these, or analogs of these guys. So citizen scientists can help us classify galaxy morphology, right? Galaxy morphology is telling us about galaxy physics. And then, this is really the big rise of the deep learning era. Sander Dielman, who actually I think is at Google, maybe at DeepMind or something right now, but did a lot of work on these rotation invariant CNNs to now classify galaxy morphologies based on citizen scientist classification. So you have all these citizen scientists who have classified galaxies, and then he could basically give you sort of propagate those labels, also maybe predict their sort of probability distributions, which ultimately help us about the task to learn about galaxy physics. Okay, so this is kind of getting more and more complicated. But my take on the matter is that ML algorithms, these machine learning algorithms, also can just bypass all these heuristics we've made up along the way. Like galaxy morphology is an interesting tool, but it's a classification scheme on something that's not actually like classes. Galaxies are not necessarily classes, right? What you see here is that galaxies actually kind of occupy a continuum of morphologies. They can take on a lot of different shapes, and it's a continuous space. They're not necessarily, well separated by anything. This just happens to be a scheme that's useful for us and has been useful in the past. But we are now at a point where we can actually, I think, move forward and just go directly to the interesting physics where we can actually predict the galaxy spectrum, right? Which again tells us about the physics directly from the images themselves. So again, a bit of my opinion here, but I think that this is one of the really important ways that our field is moving, is that we can now propagate these expensive labels of taking galaxy spectra and simply get a lot of these away with imaging. Okay. I'm going to end. This is my last slide. Bitter lesson. Who has heard of the bitter lesson before? A few of you guys. All right. Yeah. So the bitter lesson is basically that scale always wins over bespoke algorithms. It's kind of a sad thing to say. I guess that's why it's called a bitter lesson, right? Rich Sutton is a computer scientist, I think at Alberta. The idea is that like if you have a general enough method that leverages computation and you scale that up dramatically, right? Like what we're seeing with transformers now, like they will outperform your bespoke, your handcrafted engineered features. They often will do that, right? Like it's not a question of if they'll beat it, but a question of when. Okay, and this is really, really something that scientists, like physicists and astronomers hate to hear, because we're trying to learn something intrinsic about the universe. So if you're telling me that an AI algorithm is going to outperform all the things that we're making, all the physical models that we're making, which in fact they are doing, they are outperforming them in many cases, then what can we hope to learn? I think this is kind of the key question, in our age of AI-assisted sciences is how do we learn new science then if the AI is doing the learning for us, right? Like what exactly are we taking away from all this? This is really an open question. I don't know the answer to this. I think a lot of the experts in our field are either a little bit jaded by this or a little, or a little disturbed to hear that this might be true, if you even accept it to be true, of course. And so after the break, I'm going to talk a little bit more about meta science. How do we learn with AI, right, rather than have AI do the learning for us in the field of astronomy? So I'm just going to leave it there. Thank you all for listening. I guess we'll kind of reconvene in, I don't know, 10 minutes? Let's say 10 minutes, about 10:30. How about that? All right. Thank you. Okay, so in the first half, I hustled you guys a little bit because the title was LLMs and astronomy. I didn't say a single thing about LLMs. Here you're going to get a little bit more, but actually really the core of stuff that we're going to do with LLMs for science and astronomy is going to happen during the lab. Okay, so stay tuned for that. I'm going to introduce a little bit of that here as well. Just try to also jump around from topic to topic. And in fact, the first thing I want to say is actually a little bit more about my home institution. So I'm affiliated with Johns Hopkins, the Department of Physics and Astronomy. My PhD, my background is all in physics, by the way. And then the Space Telescope Science Institute, which is just up here, mostly housed in the Muller building, is just a short walk, about 15 minutes on campus. I think Sanjeev mentioned on day one that there's a nice cafe in there, Karma's Cafe. It's actually really, really good. You can get, lunch for like $7. It's pretty hard to find these days. But what else does Space Telescope have? It has a Hubble Space Telescope Science Operations Center. So HST, or Hubble Space Telescope, sometimes we just call it Hubble, is hanging out here in orbit around the Earth, and it's been up there for 34 years. So actually, just a few months older than me, in fact. And we do the science operations there. So that means that we sort of process the data, we calibrate the data, and then we sort of provide it as a service to the community. I'm going to actually talk a lot about the astronomical community here because I think it's actually kind of interesting to see when we have multidisciplinary fields to think about like almost the culture shock of what it's like to engage with a different community. I think there's a lot of things we can learn. Like we astronomers can learn a lot from the machine learning, from the NLP communities, and I think vice versa, there might be interesting insights that you find here. Okay, so the community at Space Telescope, it's a nonprofit, by the way, and we primarily subcontract out of NASA in order to operate their space telescopes. Hubble is one of them. This one over here is the James Webb Space Telescope, so Webb for short. And we actually run the mission operations and the science operations there. So again, it's basically a center for running not only the core, not only the scientific processing of the data, but actually we run the sort of the mission, like keeping the entire spacecraft afloat and kind of ensuring the health of the detectors and all those kinds of instruments that are aboard there. So we have a lot of engineers at Space Telescope whose full-time job is not to do any sort of research or anything, but actually to ensure that these things are running smoothly. Altogether, Space Telescope has over 800 employees, by the way, of which a few hundred are software engineers, systems engineers, that kind of thing. So it's really not all astronomers. We have about 150 astronomers. We actually have more engineers than we do have astronomers. Upcoming, we have a contract for the Roman Space Telescope, which I mentioned briefly. That's going to basically have a panoramic view, kind of like Hubble's, but it's going to enable to survey the sky at great scale, and that's going to really let space telescopes enter this sort of era of big data. So the Science Operations Center is going to be also hosted at Space Telescope. So it's really running a lot of these different space telescope missions. And finally, it's actually serving an archive, the Mikulski Archive, or MAST, Mikulski Archive for Space Telescope, abbreviated MAST. And that's another thing that we provide as a service for the community. So like all the data products, calibration products, and things like that. All kinds of images you can actually download from mast.stsci.edu. And so that's all sort of being hosted here. Now, Space Telescope actually has a second building. So if you've ever ventured over to the Rotunda building over in Hamden, this is about maybe a 30-minute walk. You kind of go north of campus, and then you sort of take a left onto 40th Street. And there's actually, it's a pretty cool little plaza. They do a lot of fun things in that area. My office is in here as well. In fact, my office is, I think it's that window right there. It's in there, and we have another couple hundred of folks working there. But it's a multi-use building, so it's actually worth taking a look there. They have a farmers market on Tuesdays. They have like live music every Friday. They have, like there's a whole bunch of shops and a lot of like, things you can get a lot of food to eat there. Pretty good restaurant selection. So it's a fun place. But Space Telescope is sort of distributed between these two buildings. Okie dokes. I want to say a little bit about astronomy literature. Oftentimes when we talk about language models, it's useful to think about what even is the corpus of text. I haven't said anything about text yet. So what is text in astronomy? Yeah, question first.
So I will also cover the sky image assembly, because every time I see the sky image, I'm like, I don't have the estimation of, for example, how many overlapping segments of the picture does it take to actually.
Yeah, how many overlaps? Yep. I'm not going to cover that here, but I'll say that it depends on your science goals. You might have different requirements. So oftentimes so in order to basically get all the images to co-add properly, you need to do things like calibrate the gain, what we call the flat fielding as well. There's even things like geometric distortion, because if you're slightly, if you have slight differences in angles and perspective of the spacecraft and things like that, those can all change that. So the calibration pipelines are oftentimes, a lot of empirical adjustments that have been made, over, decades of operations. We realize that these are, the magical hyperparameters that get things to co-add well for, this particular telescope. And that's oftentimes, what's being done there. But different science goals might have different requirements. Like some, you actually just want as much sky coverage as possible, which means that you want minimal overlap, which means that you have less of a handle on how to like align, neighboring frames and things like that. In some cases, for instance, at redder wavelengths, if you're looking from the ground, you actually have to look through a lot more of the atmosphere that radiates or basically has all these weird spectral features due to hydroxyl in the atmosphere. So this is kind of a mess. But like these kinds of weird small effects can actually cause big differences, because you realize, oh, when I look at red wavelengths, it looks pretty different than when I use blue wavelengths or a greener filter or whatever. And how do I co-add these properly? So it really will depend on your use case. Yeah, thanks for the question. Alrighty, so let me say a bit about text in astronomy. So I figured I would just mention this because I think that this is actually a little different than the case for CS. So in astronomy, you almost always submit to a refereed journal for publication. And so typically this is going to be it's going to be either a letter, which is usually like a high impact short result. Something like, maybe 6 pages is typical. An article, which is sort of like a regular long form, technical manuscript. And that's going to be of order, I don't know, 8 to 25 pages. It really can run the full range of these. I've seen, papers, regular papers that are like 40, 50 pages long, which are kind of a slog to read, but it happens, right? I'm not talking appendices. I'm just talking about the main body of the paper. You also have these papers which are called supplements sometimes, and they actually are complementing some data set or sometimes even a software system or something like that. But they often will present sort of a large set of tables or images, and they sort of present a lot of the systematic like sort of things that you need to know about that data set. These are kind of the main typical like ways that the astronomy literature are organized. There are also non-refereed articles, and this is a lot less common in astronomy than I think in some other fields. For instance, in like high energy physics, like a lot of things just get posted straight to arXiv, and that's that, like that's your paper. But in astronomy, you sometimes have pedagogical papers, things that are just interesting notes that people want to highlight. Those can be, posted onto arXiv, but not necessarily submitted to a journal, and therefore they're not refereed. There's no review process. Conference proceedings in astronomy are almost like never reviewed, right? So if you submit to a conference proceeding, it often doesn't count the same way as a publication does. It's not like in computer science or in machine learning, especially, where you actually get multiple reviewers, for conference proceedings or for a workshop paper even. Like in astronomy, basically there are no workshops, and conferences are usually very small, and they're typically non-archival. There are also these things called research notes, which are archived bodies of text. They're usually pretty short, like 2 or 3 pages, and maybe just a single figure. These kind of launched because we realized that astronomy was being biased against null results. Actually, a lot of sciences have a problem with nobody wants to publish a null result. But one of the things that we want to do is incentivize people to still publish, things like if they took a data set, they took, like for instance, during grad school, I went and grabbed a bunch of observations of a bunch of galaxy clusters, and I didn't find anything really interesting. What I could have done, if had this thing existed at the time, is to publish that data set anyway and say, we try to look for X, we had this hypothesis, it was wrong, right? And here's this null result. But, so that can be a research note where you just publish a single figure and say, this is like the experimental design of the problem, but we didn't find anything interesting. If anybody else is wondering, you shouldn't go down this path. That also exists for other things. People can publish research notes on other types of small things, but again, it's non-reviewed. It's very fast turnaround. They basically get published or they show up on, they become archived in a couple of days. Or even blog posts, right? I think blog posts are becoming somewhat common, or at least people often write them in computer science. I've seen blog posts cited in papers, but in astronomy, like, people can have blogs, but it's not like an actual professional, like a technical unit of writing. The astronomy journals. So there's a whole bunch of these. I'm mostly going to focus on this first one, the American Astronomical Society journals. So AAS is sometimes what we call it. That is, I'm going to say more about that in a second. There's some journals there: Astronomical Journal, the Astrophysical Journal, Astrophysical Journal supplements. Then there's also, sort of this other kind of ridiculous name, Monthly Notices of the Royal Astronomical Society. Believe it or not, that's a legitimate journal, actually one of the premier journals, very, very old and esteemed journal, the Royal Astronomical Society, which I believe it is housed in Edinburgh. Anyway, they have this monthly notices, and they've been doing these publications since, I don't want to say the wrong year, but it's been a couple of centuries, like I want to say like 16 or 1700s. They've been doing stuff like this for a long time. And then the Astronomy and Astrophysics is another journal that's sort of the mainline journal out of Europe. So these are, generally housed in the US, the UK, and the EU, sort of broadly speaking. There are other journals that we sometimes pay attention to, but not that much because they're mostly for profit, and astronomers are very averse to publishing in, for-profit journals. So Proceedings of the National Academy of Science, that is not for profit. It's just they don't do a lot of astronomy there. Nature and Nature Astronomy are run by for-profit entities. So actually a lot of astronomers have a negative reaction to those highly prestigious journals. Same with Science. It's very interesting. And then Astronomy and Computing is another sort of new journal. This is not nonprofit, but it's oftentimes if you want to talk about methods, or you want to introduce some new code or something, and you want to characterize that for astronomy, that actually is a good venue for that. Okay, so this is just sort of a highlight of a bunch of different astronomy journals. I'm going to jump more into AAS journals for a sec, but before I do, are there any questions here? All right. So, actually, yeah. So publication norms. Now, this is also quite different, I think, compared to CS or ML. So typically, if you submit a paper for publication, the editor will look at your paper and make sure that it's. Oh, hi. I'm sorry. Yeah. Yeah, it's. I mean, so we're going to talk a little bit about accessing scientific papers, later, like in terms of grabbing content from scientific papers. I've heard people just find that it's interesting to look at the different norms between the fields, but it's not directly relevant. Yeah. Yep. So, but within astronomy, so what often happens is, so here's an interesting thing, right? Like if I say archive paper, different fields will think of different types of things, right? Like in astronomy, you typically will only have papers on archive after they've been accepted, by a journal. So after multiple rounds of review, like at least the old school thought was you only put your paper on archive after it's already been essentially accepted for publication. And that's not always true in other types of fields. So you sort of have a different level of calibration of like, how much do I trust this paper if it's on archive, depending on the field. But typically, like in astronomy, you only have a single reviewer, who then basically will review the paper and give a recommendation to the editor, things like, reject or, essentially marginal reject, which is almost always the case, which is essentially like in its current form, this paper is not suitable for publication, but I recommend the authors do A, B, and C. This happens like almost all the time. And then there's sort of like a marginal accept, which is like, oh, if they make these minor tweaks, we'll accept the paper. Or technically they can accept it outright, but this basically never happens. Okay. And frequently you just go back and forth with this anonymous reviewer, over the scale of months to basically go and curate your paper. You do what they say, and then they say, okay, well, but now I noticed these other things are a problem, or you didn't go into this in enough detail, and then you go and you do that, and you go back and forth. And the editor sort of acts as a middle person to facilitate those interactions. This is usually anonymous, usually single anonymous. It can be dual anonymous. I think it would be better if we did more dual anonymous submissions, but in any event, I mean, astronomy is a very small community, so like everybody kind of knows who's doing what anyway. This can easily take 6 months, sometimes 12 months between initial submission to final acceptance of papers publication. And the eventual acceptance rate beyond that initial triage stage, right? If the editor doesn't immediately throw out your paper, it's actually quite high, the acceptance rate, something like 80%. So this is kind of also different, I think, from a lot of other fields, where you often will have a ranked ordering of like, these are the most prestigious journals, I'll try here. And if I don't get it into there, then I'm going to try a second journal. And I'm going to keep trying down the list. But in astronomy, you basically have the set sort of, these are the 3 prestigious journals, the standard journals. And they all have, a high bar. And the idea is that eventually you should be accepted. Now, sometimes authors just will be like, that's too much work. I don't want to do what the reviewer say. Because like sometimes the reviewer will say, just rewrite your whole freaking paper. It's all wrong. Or they'll just outright reject it. But oftentimes, if major revisions are required, the authors will comply and will eventually like get their paper into shape. So it's just, this is the way that our field has sort of worked. And I think there are problems with it, but it's kind of an interesting data point. Now, the AAS journals is actually fully owned and managed by the astronomical community. So, there's elected officials that govern this body, which, there's a lot of sort of board of trustees, committees, executive office that sort of all handle these sorts of things. And it's all, fully open access after they publish the papers. One of the really interesting things about this, though, is that the community really does have a say on changing, the publication norms. So I think like, we regularly meet, twice a year, the American Astronomical Society. And, there are things like discussions about, is this actually serving us well, right? Is the academic publishing, methodology, is this like just not a good system for us? And, like obviously it doesn't mean that we'll change all the problems that are wrong, but it's kind of interesting that we have this nonprofit entity that really does help facilitate, and I think that like, at least in the US, we really do support this. Like there's a unified support that we should, care for and steward and lead our community and do that well. And so this is kind of another unique thing I think about astronomy, or at least it's kind of interesting, like how willing people are to get into the weeds of this. Okay, so let me say a little bit now about bibliographic systems. So there's sort of this joke that, like, oh yeah, question?
How did difference
Yeah, great question. How many papers, do students have before PhD and during PhD? The distribution is very wide. It's also started evolving with time. I would say in the last 5 years or 10 years, it's gotten ridiculously more competitive, but I don't think necessarily in a good way. I would say that the median is definitely 0 before PhD, right, as first author. And generally first author is what really matters in astronomy. And then during the PhD, the median is probably like 3 or 2 first author papers. 5 to 6 years. Yeah. Typically a master's in the US is bundled with the PhD. Yeah. So three papers during your PhD would be considered a pretty decent, PhD. Yep.
And I could output and like that's the
Definitely not the latter. The authors can choose to make themselves anonymous or not. That's actually kind of an interesting thing. I'm not really sure why. I think it's because for a long time it was always revealed publicly who the authors were. And then it became sort of you can check a box and then make yourself anonymous. Again, I'm not really sure why it's like that, but I think this is one of those things that we're actually there are talks about changing that, right? That the default should be dual anonymous unless and the reviewer is always anonymous, right? But the author list is should probably be anonymous. It's just probably more like we're grandfathering in the old system as well. But that default should probably change. Now, one thing so it actually varies by journal too. So one thing that I find frustrating, so I review a lot of papers all the time, and like one of them is like some of these journals, they will like send you an email and be like, hey, are you willing to review this paper? Here's the author list. And I'm like, why is that the first thing you show me? And I think that really can cause biases in review. I genuinely believe it can. So at least, I could imagine a scenario in which you either if the authors even choose to reveal that it's not being revealed until the way end of the like after you submit your review, then maybe like you can say like, oh, I just don't really know why there's any reason to reveal the author list in general. Yeah. Yes. Mm-hmm. I actually don't think that there's a strong bias against sort of more junior researchers in astronomy in terms of like the papers. Like I actually suspect that there's a stronger bias against like certain countries that of origin where people are submitting papers from more than anything else. That's often what I think is the most pernicious bias with this. Now, yeah, so whatever's going on with the journals, so I think one of the problems with the journals is one of the reasons in astronomy is this. For a long time, telescope time was actually quite proprietary and a privileged thing to get. You would fight dearly to get time on a telescope. And actually, maybe I should say a bit about this. You propose for time on a telescope, right? This is actually something that often happens. This is almost always dual anonymous, and you say, I want 8 hours of observations with this 10-meter telescope that's on the top of Mauna Kea in Hawaii, and I want to make sure that it is observing my targets, these astronomical objects, so that I can do XYZ science. And you go and submit this, and it goes before a time allocation committee. These things convene all the time. So again, this proposals being put forth to go and observe certain to collect data. Now that is totally anonymous almost always, and then you get a decision on that, and then maybe you get your telescope time. Now one of the weird things about this though is that sometimes that data it hits an archive, and then some other group says, oh, I saw this awesome data set that's just on this astronomical archive. Let me go and write a paper about it real quick and scoop the original authors who proposed for it. But that doesn't necessarily they may not have the relevant expertise to understand how to analyze the data well. As I mentioned just in the previous lecture, there are tons and tons of weird biases, systematic effects, like all sorts of problems. Learning to use a telescope is not an easy endeavor either, right? To take those observations. So the person who did the observations, sometimes you literally control and determine the telescope and steer it. To take those observations, you often want them to be an author on the paper because then you trust that they did a good job of calibrating the data. But so part of the reason I think originally why this was not done blinded or anonymized for the author list is to ensure that when new observations are presented, that you actually know that the people who took those observations are presenting the data are actually those people and not some other folks who just happen to see a nice data set and maybe don't actually understand how to use it well. Again, kind of an antiquated system. It's kind of interesting and worth more discussion. But yeah, I appreciate you bringing that up. Any other questions or thoughts? Okay, so that's kind of how the system works. But let's say you have your papers now, and it now gets indexed into a library system. So NASA Astrophysics Data System, or ADS. It's sometimes said that the mark of an astronomer, like how do you know somebody is a professional astronomer, is like they know how to use this system, right? And anybody who knows how to use this system can call themselves an astronomer, because like this is just so integral to being able to do like search the literature to understand all the prior art in astronomy. And it, you know, it catalogs and indexes like, you know, basically all of the papers that are relevant to astronomy. You can kind of find it. It's called NASA ADS, but it's got this kind of weird URL. It's run partly by the Center for Astrophysics out of Harvard, so it's sort of got a Harvard edu. You know, this is kind of what a typical paper might look like when you pull it up. This is one of mine, but you basically have sort of the abstracts. It started off as an abstract service, often, you know, just as arXiv kind of did originally too. But you know, it basically will list things like the title, the author list, the abstract, which kind of goes down here. And then on the left panel, there's a bunch of other stuff like the citation graph. You can click around and quickly access papers that are either cited by or referenced within the paper. You can look for similar papers and stuff, but nobody ever clicks on that. And you can also look at things like you can export that citation to a BibTeX or whatever so that you can easily you know, link to it in your upcoming papers. On the right side, there's also some useful stuff. So you have direct links to either the abstracts or the PDFs from the publishers. As I mentioned, most of these are open access. So you should be able to access all the PDFs rather than going through some paywall, at least for all the community-supported journals. You can also oftentimes click around. If you look in this data products tab, we basically do named entity recognition of astronomical objects. So imagine you have your favorite galaxy, the Whirlpool galaxy. If you wrote a paper on the Whirlpool galaxy, then you should see, you know, under one of these sources, it should be indexed in some sort of database of astrophysics objects. And so the Whirlpool galaxy might, you know, if you click in there, it might be like, oh, this is a paper on the Whirlpool galaxy. If you click on that, you can see, oh, here's the other like 7,000 papers or whatever that talked about the Whirlpool galaxy. And so anyway, so it's just very handy. I'll also mention that the PI, basically the sort of the lead of NASA ADS, is going to give a plenary lecture on this and some other things, of course. So Alberto Akomazzi is, I think, coming in mid-July. So he can tell you all the wonderful, great things and how they built ADS and, you know, it's decades of serving the astronomical community. Okay, now, but here's one thing, right? So my name is John Wu, sometimes in publications abbreviated as J Wu. You might guess that there's a lot of J Wus in the different sciences, and maybe some of you guys are also, you know, have this problem. And so if you do a search list of author, you know, John or Wu, comma John, you have 6,000, you know, plus results here. And if I did J Wu, I think it's like 50,000 results, right? Just within ADS alone. And then, but there is something that a lot of astronomers use called ORCID, ORCID, which is just kind of a way of keeping track of your scholarly identity. And so this one's a little out of date now, but anyway, but so this is like, you know, my ORCID number or whatever, and you can actually see like it's actually only going to pick up on the papers that I've published already and that have, you know, this ORCID ID with it. So this is just a more useful persistent identifier that astronomers all happen to use. I know that there are other systems out there. I forget if Semantic Scholar, like others, you know, they might all have like their kinds of systems. This is the one that astronomers happen to use, and it's actually very well integrated with the other ecosystem of tools. So, you know, you can look on here and you can go and find my email address and see where I worked and stuff like that. It's yet another thing like a CV to keep track of. Okay. Let me go and actually talk about LLMs now, sampling of LLMs that have been applied to astronomy. So a bit in the beginning, just going to talk about astronomy literature. And then at the end, I'm going to say just a bit about multimodal foundation models that are analogous to the LLMs that we use in you know, outside of astronomy that have been used for our types of data. So way back in 2021, the NASA ADS team decided to, you know, fine-tune a BERT-like model, so bidirectional transformer model, and apply that to astronomy. So now, of course, BERT doesn't do next token prediction. It does the masked language modeling, you know, training, and it's also can be optimized for next sentence prediction. These were more common, you know, in the era of training BERT-like models. So the NASA ADS team basically grabbed all of the astronomy text out there, which is actually only about 4 billion tokens or 100 million sentences, depending on how you sort of chunk that up. And so AstroBERT has, you know, of order 100 million params, and they were able to go and you know, fine tune this model. I think the initial goals of this were to do better sort of paper recommendations and do some fine tuning on named entity recognition and being able to scrape the astronomical literature. But obviously this being published in 2021, this was a fast-paced era where I think models were getting bigger and better, and it was starting to also be realized that the neural scaling laws of transformers or of other types of models would be an important way to check against how well you're able to fine-tune your models. So 4 billion tokens really across all of astronomy really is not that much. So it's just worth keeping that in mind when we think about different techniques for to pursue NLP or large language models for astronomy. AstroLlama is sort of a more recent example of this. I know some of the folks involved with the astronomy team here are involved with the AstroLlama endeavor. So this is like towards specialized foundation models, fine-tuned for astronomy specifically. And so what I'll show, I just grabbed one of the figures from the text here, which shows, it's kind of in the upper panel. This is basically just showing pairwise cosine similarity of 2 random snippets of text from 2 random abstracts. And what you're basically finding is for blue, which is GPT-3 embeddings, and then for red, you're seeing the AstroLlama embeddings, the specialized fine-tuned but much smaller model, is that you're actually seeing greater diversity in the AstroLlama embeddings, right? So they're sort of spreading out over there's sort of a larger distribution of pairwise cosine similarities, which is whereas for GPT-3 it just says, oh, but all astronomy is kind of related to each other, which is fair to say because it's meant to be more of a general purpose semantic search. So in this case, the authors can say that this at least gives you more fine-grained embeddings for astronomical concepts. Another thing, this kind of illustrates the example a little more clearly. So if you're an astronomer, you would recognize that papers 1 and 2 here, astrophysics, gyrokinetics, kinetic and fluid turbulent cascades in magnetized weakly collisional plasma, versus another paper, which is comment on modified Coulomb law in strongly magnetized vacuum. Okay, so they both have the word magnetized. One is the American spelling, but the GPT-3 cosine similarity score is very high. But if you're an astronomer working in these fields, you'd actually recognize that these are actually pretty different topics, right? In fact, the second one is probably not even related to astronomy at all. That's more like physics. In sort of, yeah, that's more like a physics problem. I'm not actually sure that's in astronomy whatsoever. And then paper 1, and then this other example here. So what happens is GPT-3 gives that similarity score of close to 80%, whereas AstroLlama gives it something like 36%. And then the second example shown in blue says, a Spitzer census of the IC 348 nebula versus paper 2 says sequential and spontaneous star formation around the mid-infrared halo H2 region KR14. Some named entities are going on in there. That's always a challenge for your tokenizer. But these are actually talking about sort of star-forming nebulae. And so those concepts are actually very similar, and AstroLlama does a good job of assigning similar cosine similarity scores. But GPT-3 is kind of about the same as before, about 80%. So it gives you a little more fine-grained nuance in the embedding space there. Again, this is AstroLlama is trained on a relatively small corpus of text, so it obviously has its limitations. But one of the other things that kind of came out of this work was AstroLlama Chat. This is kind of an instruction-tuned model so that it can answer QA pairs, question and answer pairs about astronomy questions, which were sort of generated by taking the actual astronomy papers and then having GPT synthesize questions and answers for them. So that sort of is a more conversational model. You can actually ask it proper questions. There's actually like a Hugging Face endpoint that you can play with that if you want. Yeah, so and a number of members on our team, the Astronomy LLMs team, have been involved in this kind of work. So definitely chat with them if you want to learn more. Okay, yeah. Actually, I'm going through this very quickly. So then I just want to talk about multiple modalities too. So you can actually do things like clip, this contrastive pre-training method of 2 different modalities, and you don't have to do this with just text. You can do this with any 2 encoders that go and share into a similar latent space. Okay, so in our case, if we're interested in astronomical images, but we also want to align them with spectra. You can actually learn encoders for both of these. So in this case, this is kind of like a transformer-based model, and here you're going to use some sort of, either a vision transformer or a CNN or something like that. And you can actually have them encoded in the same space. As usual with CLIP, this is based off of CLIP algorithm, where you're basically looking to match the pairs together and separate out the non-matched pairs and ensure that they come up with similar latent representations. The idea is that the shared embedding space actually tells you something about the physics of these two objects. So this galaxy, actually, this is the spectrum of that galaxy, right? Yep.
So the spectrum is like very important. For example, the I can do like even with the peaks or we have too many samples. So it's like it is the way that's not where I can figure it out.
Yeah, so actually, yeah, so we that I should mention, so this sort of is really a 1D, like this is a 1D sequence, right? Where the intensities are very high. So you're saying are some of the peaks are just too high and they need to be clipped out? Oh, uh-huh. Yeah, I mean, we typically log scale everything. That generally puts it on the same front. I mean, I do think that there are some. I'm trying to think if there's like a canonical way to do this. Sometimes what you do is you normalize everything by the continuum of the signal. So sort of like where most of the flux is. This is what we sometimes call the continuum, and that's sort of dictated by the stellar light. And so if you normalize by that, you often end up with a bit more of or smaller dynamic range. But I agree, yeah, there's sort of extra degrees of freedom. Yep. What is the signal? Yeah. So right. So okay. So what we're doing here is like let's just look at the red boxes. So you've got an image of this galaxy, and then you can actually take all the light, add it up, and then disperse it. Like I said before, like imagine you disperse the light through a spectrum or through a prism, and then so you basically can measure exactly how much light there is at every single specific wavelength. And so that's what's being shown here. There's no axis, I'm sorry, but on the y-axis of the upper panel, then you would have something like the flux per little bit of a spectral bin, right, per wavelength unit as a function of wavelength. So it's really just a 1D sequence of intensities. Yep. And there are versions of this where you can, sort of generalize to multiple dimensions. Yep. Oh, because I already did that, and this needs to be a new paper. No. Yeah, I mean, no, I mean, yeah. So I did the thing that you just described, which I think has a lot of good use cases. Now, one of the things that you can do here is actually you can sort of sample from the latent space, or maybe even if you have a sparse sort of representation of this, you can maybe still be able to index into that latent space and grab out corresponding spectra if you have an image. That's usually going to be the kind of case you have here. But yeah, no, it's a good question. I mean, there are probably also hybrid approaches where you're doing both. Yes.
How these embedding spaces result when you have a third modality? It features the text and image.
Yeah.
Space, the spectra, the text, those are the space. And then all of a sudden you're connecting all of these modalities.
Yes. No, that's a really good point. Yes, if you can get a third modality like text, that would be extremely powerful. Now, I know this first author, Francois Lanous. They wanted to do this, but the amount of paired or triplets of data is actually very expensive to collect and to get all those in the same space. So right now, it seems like that's the biggest limitation is we need to annotate more data or ensure that they're put together. But I agree. I think that would be a really powerful representation. Yeah. And in fact, so I think I mentioned Galaxy Zoo earlier, or the Zooniverse Citizen Science Project. So another thing that they have is actually for a lot of galaxies, the citizen scientists could have either put up originally started as hashtags for each different types of galaxies, just like different types of feature representations. this is a very, very sparse vocabulary, of course. And so I'm not sure it's enough to really get us to train something like a CLIP, trimodal, embedding space. But you can imagine getting text, or at least bootstrapping your way up from something like that into more full sentences or things that are, whatever. Anyway, there's probably a lot of interesting avenues for exploration. I'm sure you guys can think of a lot more clever things than I can. And so one of the use cases then is shown on this right side here is like, imagine you actually only have this this. Wait, hold on, sorry. Oh, in this case, yeah. So you have okay. So imagine you have this image. I'm trying to think of which one is actually meant to come out here. Yeah. So imagine you have this image, right? Images are cheap. If there's one takeaway you should learn about astronomical data, it's images are cheap, spectra are expensive. So oftentimes you want to get spectroscopy of things in order to, again, learn about the physics of that thing. And so here's an image, right, of a galaxy, and it's being put through the encoder, and then you can do, whatever your favorite similarity search in that embedding space and yank out this candidate spectrum. And then actually from that candidate spectrum, this is, the attempt to do zero-shot learning of new galaxies. If you trust your embedding space and basically the spectral encoder, then you can actually just take that spectrum outright and then derive a bunch of physical properties for that galaxy based on that spectrum. Now, in practice, it's a very tricky business. It's going to be really hard to convince astrophysicists to believe the kinds of results that you get. But there's no reason why it shouldn't work. Scaling this up, if you have good, high-quality paired data, and you've tested out on your validation sets and things, we do expect this to be a useful and valuable technique. So I think that this is something that moving forward we're going to want to do with just totally new frontiers of data. Yep.
I guess we found the scientists give it an image, and and the system gives him back a spectrum and says this is the spectrum of the image. The scientist will be like, obviously not, this is made up. But if you say this is a spectrum of a very similar object, get inspired by the spectrum. It's like maybe.
Yeah, no, that's true.
That might not be as much.
Yeah, no, I agree. The framing is important. I mean, a lot of the endeavors of using AI in science, using machine learning in science fields is a question of framing, right? And I think there is, there's a very real fear that, people will apply ML in sort of just random ways that they don't really understand, and AI, same thing. And so I think that being able to be very clear about what it's doing and explicate that, I think is also a good way to build trust for our community. Again, I'm talking a lot about community, but I really think that, for a lot of folks, like a lot of the folks in this room, you guys are leading the charge in building trust for these kinds of AI models. So it's important that you know how to communicate that trust as well. Yep. Yeah. Yeah, so in this case, this is so at least in this figure, this is just it's just indexing and grabbing another spectrum. So it's not really prediction so much as just grabbing the nearest neighbor. There are versions of this. So are people familiar with normalizing flows? No. Okay. So there's you can imagine that there's another thing which, instead of having the spectra encoder as just sort of this one-way encoding, you can almost think of it as an auto encoder of sorts. But it's really more like a mapping of the probability density function from this distribution, from the embedding distribution to some actual observed distribution, basically, of data. And so you can sort of make sure that the flows match together and with normalizing flows. And if you can do that, then what you can actually do is you can essentially interpolate in that space, both in the candidate spectra space as well as in the embedding space. I forget if this paper, I think their updated variant does do something like that, but not in this figure. Yeah, good question. All right. Any other questions? All right. I think I'm getting close to the end here. And so the last thing I think I want to talk about is this paperclip algorithm, which is actually quite similar to what I just described. again, you have an image encoder, but this time you actually have a text encoder. And so this is going back to the idea of writing proposals to get observations. So if you submit a proposal for the Hubble Space Telescope and it's accepted, your proposal abstract actually gets archived in our proposal system at Space Telescope. So here they take all of the Hubble proposal abstracts that were accepted over 34 years of observations, and then they actually look at what it ended up observing. So this is kind of a unique way to do this, where you've now got the text, which has some very technical description. It says, we propose wide field camera 3/UVIS, F336W, blah, 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 observations for 8 luminous infrared galaxies in the Great Observatory's All-Sky LIRG survey scheduled for JWST Cycle 1 observations with a proprietary period of 0 days for 50%. So anyway, so it kind of describes the observations, some metadata about the observations. It describes, the actual science goals of the program, and actually some description of the targets that it's trying to observe. And then so that happens, we assume that this has already been observed, and then you can go and look at the corresponding images that have actually been taken. And then you want to now align those two things. So now this is real text and actual images directly from Hubble, and you put them into an embedding space again. And so one interesting thing, I think this is more of a proof of concept, is that you can actually now retrieve observations, based on, basically this is a way to search by observations via natural text. So if you can query something like a barred spiral galaxy, you can go and look in the text encoder based on all the pre-training, the clip-like pre-training, and again, try to grab and sample the observations that are coming out. That gave you a barred spiral galaxy. And in almost all, I think in basically all these cases, these look like pretty barred spiral galaxies. Although this last one down here doesn't look so convincing to me. Yep.
Like for telescope data?
Yeah, in a ways, yeah. And I'll say, yeah, it is. And the MAST team, I think, is interested in doing something like this. So Josh Peak and several others have worked on this kind of thing before too. We've done things that are like search by image, things that are like search by text, but usually those have to be kind of hand coded up till now. And people will write down keywords and things like that for proposals. So all these things, already, it's not like there is no prior art. But this is one of the first, this paper at least is one of the first sort of end-to-end ways of doing this with essentially nothing but large models in the data. All right. Any other questions? Oh, yeah. We're really limited by actually the amount of data. Like we just don't have that much data, right? Because all these proposals and things like this have been painstakingly written by humans, and then these time allocation committees, like we spend 40 hours or something reviewing these proposals, right? You basically take an entire week and you sit with a group of other people in a room, now on Zoom or whatever, and you just read hundreds of these proposals, right? Maybe not hundreds, like dozens, to maybe hundreds depending on the panel. And we do this not only for observations, by the way, but we do review panels, for all sorts of different things, for giving grants, for promotions, whatever, life of faculty member. But you end up, the things that end up getting accepted and archived in this system is pretty small, right? So I think that's the big problem, is it's really hard to, you want to come up with a data efficient way of constructing these representations. I think it's still an outstanding challenge. All right. Any other questions? Thoughts? Great ideas? I want to say, oh yeah, okay. So that's kind of it. And I just want to give a sneak preview of the lab. I don't think this is going to be anything dramatically new for you guys, but it will be helpful for, getting you set up with a lab. And just some motivation, not that you really need this, but of course, LLMs we know are prone to hallucinating. They just like to invent plausible sounding information. And this is, something that we care a lot about, of course, in science and astronomy. I mean, you care about this everywhere, of course, but in science too, this is one of the big reasons I think why a lot of the old guard in astronomy are very much against using AI in any capacity. And so you can imagine that one way that you want to mitigate hallucinations by forcing them to retrieve from some trustworthy source and make sure that they actually cite that source and then generate text only surrounding based on that source. So here's an example. This kind of ties together actually some of my background, which is in radio interferometry. I worked in a computer vision lab way back in the day when I was an undergrad. But I asked a question to a system which can perform retrieval augmented generation. I asked this, how can compressed sensing be used for image deconvolution in radio interferometry? So that's a lot of jargon. Only radio astronomers will probably understand what that means. Then you can see that it generates this response here. This is in the form of a Slack bot, and this is actually exactly data that will be used as part of the evaluating LLMs for astronomy research group. So again, talk to the team if you're more interested about this. But it generates a plausible sounding response. It's actually a pretty good response. But it also, importantly, cites some papers here and that it's actually pulled the data from. And so this is kind of the goal of what we want. And we, of course, also want to be able to evaluate how well these systems perform. So just a quick schematic of what we're trying to avoid. You have a user query in this, kind of black box up to the left, and then it goes through some generate LLM. If you just have it generate some text, you create some response that might be prone to hallucination. But instead, what you want to do is come up with, in this case, a very simplified approach to RAG, retrieval augmented generation. I think you guys, know more about this than me in many cases, but and yesterday's lectures and lab were very useful. But just kind of to recap, right, you got some encoder language model, which can go and map that user query into a high dimensional vector space. And using that same encoder model, you now have your library, your data sources. In this case, it will be archive papers, or maybe even just the archive abstracts to start. And you can go and convert that into the same latent space. So you're now kind of representing them in the same high dimensional vector encodings. Based on that, you can now perform a similarity search between the user query initial question and those document representations, which allows you to quickly search through that, basically index out the documents that match best. So if you can quickly index into this library of archive papers, there are about 300,000 astronomy papers on archive, you can then quickly fetch additional data or context or metadata, like maybe you might be interested in the year of publication, you might be interested in some other sorts of things that you don't want to match on, right? You don't want to perform similarity search on your date of publication or the author list necessarily, but maybe you do want to grab that data for some other purpose. So you can quickly grab that and concatenate it in with your abstracts, and then feed that all alongside your initial query, as part of this retrieval mechanism. And once that's all concatenated together, now you've got basically something that you can go and send into a generator. The thing that I want to the reason I bring this up now is because this kind of everything in this blue box, your IR system really can be whatever. And in the case of the lab in the afternoon, we're going to talk about using the archive API. So the archive API provides an endpoint where a REST interface where you can actually go and query, basically launch query terms into archive and grab paper abstracts and other metadata. And so you can go and kind of change everything within this blue box and still perform your retrieval augmented generation. So I look forward to seeing the kinds of solutions you all come up with. But of course, this is just one way to do it here, where you have a locally hosted document database. You can cram that all into a generator and then construct your final responses. Any questions on that? All right. This is all familiar to you, right? Good. So, of course, you can also do things like, change up the prompt. You can kind of, try to direct the LLM to be sort of more strategic in how it answers and so on. These are all things that you can play around, again, with the lab. So, again, I urge you to be creative. You do not have to stick to the exercises that are within the lab. Those are just meant to help guide you, but you should spend your time in ways that you think are interesting. And so if you see opportunity to make a scientific LLM or RAGBot or whatever do better, then by all means go ahead. I'll also just say one last thing. There's also sort of code that, well, it's not in the lab, but if you're interested in deploying this as an actual Slack bot or whatever, I've already set up a lot of the backend for that. or at least I have a guide for putting that all together. So just get in touch with me if you're interested in deploying like something like the Slack bot. But otherwise, right now, the lab is all can be done on Colab, so you don't really have to serve up anything or have any, server listening for Slack responses and whatnot. Okay, so I think I'll just leave. We have plenty of time for lunch for y'all, but I'll just leave it here and take any final questions. Yep. Question. Yep.
For LLM in astronomy, like brainstorming research topics, is that, or like, I don't have a good sense of what types of questions.
Yeah, this is a great question. Like, so people have looked at things like, hypothesis generation, or, you might want to, I don't know, like another thing people are interested in doing is like, if you want to convene a review panel, you want to match, human expertise based on like maybe like the last 5 years of papers that they've published. You want to prevent information from getting stale. There's a lot of kind of real world use cases that we potentially could do. And I think that we're sort of on the verge of seeing a lot of these being launched right now. I think that there's probably some opinions that can be voiced here too, right? Like there's the saying that like, I want AI to do my laundry and dirty dishes so that I have time to write creatively and make art. I don't want AI to make my art and creative writing so that I have to do my laundry and dirty dishes. I think that we should think also about what are people asking for? Like, what are the things they don't want to get done, right? A lot of times, people start startups because they find a really difficult and annoying problem. Like there's like, oh, there's this stupid thing that's always bugging me, right? This painstaking process. And then they come up with a way to circumvent it. And that often is how you launch like a new business, right? Like CEOs or whatever are like so convinced that like I see a preferred future which bypasses this dumb, annoying step, right? In between. And I think that in astronomy and in science, in our fields, we need to think carefully about our field. What are the things we like to do? What are the things we don't like to do? And what are the ways that we can leverage AI to sort of bypass that? And I don't know. I think a lot of opinions, can differ here. Yeah.
I wanted you to say a bit more about your team for the summer and what the summer plan. So I know you're going to do a lab, but if you could say more.
Yeah. So our team is really multidisciplinary, right? So I think we kind of draw from a variety of expertise. So some of us are astronomers who have minimal experience doing NLP or working with any sort of text data. We have folks who have not done any astronomy whatsoever. And so what the team is interested in, I think, is primarily twofold, right? One is evaluating the LLM, so performing a good evaluation study on how professional astronomers are interacting with the data here, right? And the data in this case are basically these question-answer pairs being generated, as you see here, with an LLM. So how are astronomers learning to use LLMs? How do they build trust in LLMs? How do we know that they're actually doing a good job of answering questions? And are astronomers like actually finding this to be useful? So there's like a lot of that study, I think, is going to be led by folks who are more well versed in human-computer interactions and understanding, how to really conduct interview studies and evaluation studies when in this kind of a system. I think there's a secondary component, which is also just like how do we with that sort of data in hand, how do we also make this a better system, right? And so a lot of those can come on the heels of improving the retrieval system. It could be, really trying to understand like, how to fine tuning or instruction tuning, or there's even these new things like memory tuning, if anybody's heard of that. There are different methods now for trying to really work on these low data regimes, like astronomy. There's really not that much data out there, not that much text. But how do we improve our system so that it can work well in that? And so we have a bunch of sub-teams, folks who are interested in the retrieval part, people who are interested in, the evaluation side of it and constructing new data sets. And I think that we're going to try to attack that problem from two angles there. All right, awesome. You have an extended lunch break. Thanks for listening.